I have this test scene set up here with 40 shapes connected in series. This is a pretty fun one. It gets very chaotic when you speed this up. But as fun as it may be, that's not its purpose. So this scenario is meant to strain the system, and it gives us a starting point to try to optimize the game now. So if I enable some 5 test samples here, if we run this again, now that I got serialization working, we can copy the scenes and rerun them identically. So now we ran that scene 5 times, 2 seconds each, and we got these average FPSs. So this gives us a starting point at 44.2 FPS. So now let's try and optimize it. Alright, I got one optimization in place. This one cannot really be tracked by the FPS tester though, since it's only noticeable when you zoom out. So you see, we have the 44 FPS there. Now if I enable this change, before I was drawing 100 vertices for each orbit line, but now I have a dynamic one, so it's between 10 and 500. So when you zoomed in, it's a bit worse now even, but I'm getting to there. Now when you zoom out, we're getting 3 times the frames. You can kind of see that the vertices are getting less and less, but yeah, I think that's a good balance. So now I'm gonna try to prevent drawing orbits that are outside our screen. All right, I've successfully implemented another optimization. So with help of AI, we can now see the center of the orbit. And I'm visualizing that here in this scene. So we have this yellow dot. Now it's in the center of the planet since it's circular. But if we skew this orbit, then it nicely shows the center of the orbit. Using that, I made this nice paint illustration. The square is the screen. The circle is the orbit that's outside the screen, but how do we know if it's outside the screen? So the idea is that we don't draw them at all if they're outside. So we can easily get the distance from the center of the screen to the center of the orbit now, which are the 2 white lines. And then the maximum distance from the center is the diagonal. So if we step that far on this line, on that way, and from this way, the maximum distance from the center of the orbit is the semi-major axis, and we already have that calculated, so we just step out from that side. And if these overlap, then we draw it. And with that optimization in place, let's run the sampling. You can see 175, that's a huge improvement. Nice. So it's a bit weird with the first one, it's zoomed in, but I think that's fine. So 171.9 is our new score to beat. Don't draw orbits far away. Make sense? Alright, very nice. I upgraded our function to check if the orbit is outside the screen, so now it also checks if it's inside the orbit, but the orbit is still outside the screen. So I have this test scene set up here. This is the simple rocket orbiting the planet. You can see if the orbit is drawn, we have the yellow dot inside, but if I zoom in slowly, there it disappears. And I also realized I need to make this take the line thickness into account. So if we make the orbit really thick, then look at the white yellow dot, and oh, it's a tiny bit shown, and then boom, gone. So that's perfect. Reset that. And it's time for another. No, I was gonna show you how I did it first. So I made another paint illustration. So the worst scenario is if the semi-minor axis, which is the smallest radius of the orbit, is 45 degrees, or if it lines up with the screen resolution rather. So we have to assume the worst case. So it's not a perfect function, but it does like 95% of the job, I'd say. But anyway, we have the distance from the center to the edge of the orbit, the semi-minor axis. That's the white line. Then we subtract the distance to the center of the screen, orange, and then we subtract the distance that is the diagonal that the screen is currently showing, like in the world. So if it's zoomed out, that value is larger. It matches up with the orange. And then we see if that's less than 0, we know it's overlapping. And like you saw, that's working. And this means, you guessed it, we can run another FPS sample. Very nice. Happy with that. 279.1. Don't draw orbits. We're inside, but they are outside. I don't know. All right, another optimization in place. This one will also not be applicable for our FPS test, but this is basically it. So we're checking if the segment of the orbit we're watching is basically flat, then we just draw a straight line instead. And we don't do the stepping. Because as you zoom in, it's going to go closer and closer to this 300 vertex ellipse drawing, which takes a lot of frames. So let me show you. Here's a normal orbit, and then as we zoom in, you can keep an eye on the FPS, 500 and then 1000. Now we're very close, but this is a small orbit, so let's change that. Speed up time, get up to this part, and now we get the change already there. And I did exaggerate it a bit so we can see it flicker a little bit when we zoom in and out. But that's gonna be unnoticeable and give a lot of extra frames in a lot of scenarios. I'm sure there's a better way to draw parts of the ellipse, but I'm afraid of trying that because like what if you're in this scenario? Like I could try and find this side and then stop there and stop at this vertex, but then how do you deal with this vertex? Yeah, seems tricky. Maybe I'll come back to this in the future, but this seems fine for now. This is a good one. I profiled the FPS test, and it seems a lot of time is spent on getting the mass of a shape, which was a surprise to me. It seems to be the Pymunk don't cache it or something. But anyway, now I'm caching it, and only having this change. Let's see the effect. 332. That's a pretty nice improvement. Cache mass. Beautiful. Love easy wins like that. I got some more occlusion culling implemented. So now for any shape, we're also checking if it's impossible for it to be on the screen. And that's implemented here in the draw function. We simply skip it if it's outside the view. And let's see what we get with this change. Oh, that's looking good. 396. I'll take it. Very good. Normal shape, occlusion, culling. I refactored the occlusion culling so they all go through these functions now. And I added another optimization for when you zoom out and you see a lot of things. Here we have 145 frames now. But if I turn on this thing, which checks if they're too small to see, we get much more FPS. I have increased the threshold a bit though, so we can see the effect. So it's generalized based on the biggest radius each shape has, which works for both the orbits and any shape. But this should be 0.5, and then you shouldn't even be able to tell. And the occlusion culling for the regular shapes is the same thing. We take the distance from the center of the screen to the center of the shape, and then we have this feature called the bounding radius, which gets the largest radius for any shape. We add that to that distance, and then we add the diagonal, and then we see if they overlap or not. So that's what I generalized into those two functions. Good morning, it's time for some more optimizations. In this table, we can see that a lot of time was spent getting the position. We have 24% just getting the distance between points. So I've now implemented a way to cache the position as well. And after every physics step, we update that position there. Otherwise, if we do the gravity teleport, they're updated directly there. And let's run the test. This is a really nice optimization. 634. Let's go. All right. I made a general function to put something on cooldown. So now we can limit how often we want to trigger something. And I apply this to our gravity update parent. So previously we were checking every frame which gravity parent each object should have. That's a bit overkill. Once a second is more than enough. And let's run the FPS test and see what we got this time. This is a pretty big optimization, I think. Oh yeah. And we beat 1000 frames. Very nice. I want to show you how I draw these orbits now. Previously, I would calculate the vertices every frame, but now I calculate the relative vertices to the center of the orbit in a controlled way. And I do it every 50 steps now, for example. So as we zoom in, it's going to request more and more detail. And if thrust is applied, then the orbit is invalidated and it recalculates. So now if we zoom in again, it's going to have to redo all of those relative vertices. Very nice. We can also control how often we want this to happen. So let's set it to 5 FPS. Now you can see if I go prograde here, it goes like that. I think 60 FPS is pretty good for that one. And here's how I implemented the rounding of the steps, and then we call the relative vertices for the orbit here, and this is where we implement the cache. And that's the print statement gone right there. Very cool.